Hey, hello and good morning, everyone. Let's wait for a few more people to join before we start. So I'll start in 1 or 2 minutes. Okay, so while we're waiting, I'm just going to tell you a few points. So it turns out today is our last session since next Monday is a holiday. I was originally going to talk about verifiable secret sharing, but now I'm just going to give you a link about it and mostly just talk about our final project. One other point is that please take part in the SFQs, so the student feedbacks. It's actually pretty important because this is the first offering of this course, and whether the course will be offered again will really depend on the feedback that we get from you. So if very few people take part in the SFQs, we will not offer this course again next year. So if you like the course, please take part in the SFQs. And today I'm going to mostly focus on some of the most common problems that we've seen in homeworks 4, 5, and 6. And I'm going to also talk about the final project and basically the expectations that we have. So, okay, there are still very few participants. So let's wait for 1 more minute and then start. So, contract, and I'm going to transfer this all. So I just want to show you one of the most common problems that happened in homeworks 4 and 5 and show you how to avoid it. So just as before, we just copy this thing here. And let's say I have a contract. Let's say I call my contract C. And suppose that I give my contract some amount of money. So suppose that, for example, the contract has at least 2 Ether. And let's say I have 2 addresses here. So I have address payable. Let's call them Alice and Bob. Okay, and let's also say that I have a function called setAlice that gets some address. And what it does is that it just puts it into Alice. And let's say I have a function called setBob that just gets another address and sets Bob to be that address. And let's say I also have a function which I call payment. And what it does is that it just pays both Alice and Bob. So it says Alice.transfer, let's say 1 Ether, and also Bob.transfer 1 Ether. Okay. So this is a pretty simple contract. And actually, it doesn't have much security. Anyone can set the values for Alice and Bob, and then anyone can call the payment function. And the payment function would just send 1 Ether to either to both Alice and Bob. Now, I'm writing this contract because I want to demonstrate a vulnerability that existed in many of the submissions that we got for homeworks 4 and 5. And the vulnerability is basically due to this transfer here. So let's actually deploy this contract. So I deployed it. This is the address of my contract. And actually, let me do something else. Let's say that this set Alice and set Bob are payable. So deploy this again. So what I can do is that I can set who's going to be Alice and who's going to be Bob. And then I can just click on payment, and 1 Ether should be paid to each of Alice and Bob. Now, what I'm going to do is that I'm going to say, suppose Alice is itself, or this address is itself another contract. So let's say I have a contract called Alice. Okay. And let's say it's just an empty contract, doesn't do much. So I'm going to deploy Alice. Now, I take the address of this contract Alice, and I use it to set Alice in my original contract here. And let's say that I also pay it some amount in Ether. Let's say I pay 10 Ether, and I set Alice. Okay. So everything was fine, everything went through. And let's say I want to also set Bob, so I just take this second address here and I say this is Bob. Okay, so again, let me pay another 10 Ether and set Bob. And this worked as well. Now let's see what happens if I call payment. So I call payment. And as you see here in the log, the transaction was actually reverted, so it failed. And yeah, it says transaction mined, but execution failed. Now, what happened here? Basically, what happened was that we called the payment function, and it first tried to transfer 1 Ether to Alice. But Alice is a contract. And whenever you transfer some money to a contract, it will call the receive or fallback function of this contract. But in this case, this contract did not have a receive function or a fallback function. So when we sent money to this contract, it just triggered an exception. And when you trigger an exception in transfer, the exception basically just cancels the whole transaction. So there was an exception here, so the whole call to payment was canceled, which also means that the second transfer did not go through. So if I look here at Bob's balance was 100 Ether before, and it's 100 Ether now. So Bob is not paid either. So why is this a problem? Generally, if you have a contract, for example, in homework 4, we had a rock, paper, scissors contract. And if there is some part in your contract where you're transferring money to some person and then immediately after that transferring money to someone else, what happens is that if this person is a contract like this, so a buggy contract that doesn't have a receive function or a fallback function, then it would throw an exception, and it would also make it impossible for this person, for Bob, to get their money. So you have to be very careful with the way that you use transfer. And actually, a very similar thing would happen if I just have a fallback function that throws an exception. So I can have something like this. Okay, again, I have to set the visibility. Let's say it's external. Okay. Okay, and let's say here, instead of throw is old, I just say require 1 is equal to 0. Okay. So if I have a fallback function like this fallback function always throws an exception. And basically what this means is that if Alice is some malicious smart contract that wants to make sure that Bob is never paid, what she can do is that she can just set her fallback function to be something like this that always throws an exception. And then this contract or original contract is vulnerable because it can never pay Bob. Now, how can we fix this? Well, generally the way we fix this is that we say, well, there are several fixes. I'm going to just show you one. But we've already talked about the differences between transfer, send, and call. And if you remember, we said that if you use transfer and an exception happens, then the exception will also revert the current function. But if you use call or if you use send, then the way it works is that it gives you some Boolean value that tells you whether the call or the send was successful or not. So you can use that Boolean value to then check if the payment has gone through, and even if it hasn't gone through, so if I just had send here without even checking the Boolean value, if this send fails, this send will still go through. Okay. But more generally, one thing that we do is that we usually have only one payment function in each of our contracts. And conceptually, the idea that we advocate for is that don't pay anyone in your contracts, just let them come and take their payment on their own. So what do I mean by this? What I mean is that instead of just saying I transfer the money to, let's say, Alice, or I transfer money to Bob, in my contract, I can just have some mapping that tells me how much money the contract should give to Alice and how much money the contract should give to Bob. So I can create a mapping, and let's say that this is a mapping that maps addresses to uint, and I'm going to call it balance. So this is the amount of money that, so I'm thinking of my contract as some sort of a bank now, and the balance is the amount of money that each person should get paid. So here, instead of actually transferring the money to Alice, I would just increase the balance of Alice. So I would say the balance of Alice increases by 1 Ether. And here, instead of paying the money to Bob, I just increase the balance of Bob. And now the way that the payments actually happen is that I will have another function called claim payment, which is public. And basically the idea of this function is that anyone can call this function and get their balance. So I just say that, let's say the receiver is the person who called this function, and then I just say receiver the transfer balance of receiver. Okay. Now, why am I doing this? Because I don't want to have several transfers coming right after each other. So now if the receiver is a contract like this, if the receiver is a malicious contract that doesn't have the right fallback or doesn't have the right receive function, then nothing bad happens, right? So here it throws an exception, but that's fine because I don't care. This exception would just cancel, like revert the execution of claim payment, but that only affects Alice herself. It cannot affect Bob or someone else. So this is good, but we have to also make sure that we don't have reentrancy. So in this case, it's just enough to set the balance of receiver to 0 before doing this transfer. Okay, so, but I now need the value. So let's say the value that I want to transfer is the balance of the receiver. Then I first set the balance to 0, and then I transfer the value. Now, This has another good side effect as well. And the other good side effect here is that if this transfer fails for any reason, if it throws an exception, the whole claim payment will be reverted, which means that the balance of the receiver will not be zero, and it will also be reverted to its original value. So as long as the payment has not gone through, the balance is not updated. Okay, so this is usually how we would pay, and actually it's also possible to use call here. It's more recommended in general to use call instead of transfer, but this works fine as well. So the thing that I want you to really make sure when you're writing smart contracts is that make sure you keep track of the differences between transfer and send and call, and especially be careful that transfer can throw errors, can throw exceptions, and these exceptions can revert the entire function that you're in. So make sure that it never happens that, for example, Bob's money gets stuck in the contract because Alice is causing an exception in her fallback function. Okay? So this was actually the most common problem that we had in homeworks 4 and 5. Okay, let me now go to the final project. Just a second. Now I want to talk a little bit about the final project that you have to submit. By the way, the deadline has been extended a little bit, so you can see in Canvas when the actual deadline is. So the first thing I want to talk to you about is the rules. We've gone through this before, but unfortunately, there were a lot of cases where I had to apply the zero tolerance policy in homeworks 4 and 5 and give the students a grade of F. I don't like to do that. So please make sure that you don't discuss these problems with your classmates. Make sure that you write your code and your solution entirely on your own. And what that means is that you cannot copy from some GitHub repository, for example, or you cannot just Google it and find the solution. You have to write your code on your own. So this being said, let me actually go through the project and talk to you about what we want to do here. So the project starts by teaching you about what we call eCash, which is kind of a cryptocurrency that was invented by David Chaum back in 1983. And this is, in a sense, a centralized cryptocurrency. So we have some sort of a central bank. Of course, the way we're explaining it here, the bank has 2 different branches. It has a branch in Paris and a branch in Berlin. But it doesn't have to be like that. We can have a bank that has just exactly 1 branch. Now, the way this thing works is that the customers can deposit money in the bank. And whenever they deposit money, they always deposit multiples of some specific amount. So, for example, they always deposit multiples of 100 euros. And the idea is that whenever we do a deposit, we want to have a certificate of deposit that shows that we have actually deposited the money. And then we should be able to give this certificate of deposit to anyone else. And then that person should be able to withdraw the money. Okay. And more specifically, what we want to have are these 2 properties. We want to make sure that we have privacy. So if I go to the bank and I deposit some money and I get a certificate, and then I give this certificate to you and you go to the bank and get the money back, the bank should not be able to connect the deposit to the withdrawal. So from the point of view of the bank, all the deposits should look the same. And whenever someone is doing a withdrawal, the bank should be able to verify that, okay, this was this was there was no double spending, and that this person gave me a valid certificate that there was a deposit at some point, but the bank should not be able to say which deposit it is that is being withdrawn right now. And then we actually give a protocol that can achieve this. So let me just go through this protocol super fast. The protocol actually uses what's called blind signatures, and in this case, RSA blind signatures. So because we're using RSA signatures, we're going to have a modulus n. And just to remind you, in RSA, n is just a multiplication of two really large prime numbers. And then we have a public key E, and we also have a secret key D. This is exactly like the lecture that we had on RSA. And now here's the thing. So the way this whole system works is that you create a bill. So a bill or a banknote in our case is just a simple string. So it's just this. It's a string that says this is a bill issued by blah, blah, and the serial number is something. So each bill or each banknote has a serial number. And the idea is that if I can come to the bank and show the bank some valid bill, and if I can also show them that they have signed the hash of the current bill, then the bank would be convinced to give me 100 euros. Okay, so this is the whole goal. Whenever I want to do withdrawal, I want to just go to the bank and I want to say, here's a bill, and also here's your signature on the hash of this bill. So this ensures that you as the bank have promised me to pay this amount. Okay. But now the problem is that we don't want the deposits to be connected to the withdrawals. So in a sense, when the bank is giving us the signature, when the bank is signing a bill, they shouldn't be able to see the bill. And this is the part that is a bit counterintuitive. So the bank has to sign the bill, but we don't want them to see what they're signing. And it seems very weird, but actually it's doable. So how is this possible? The way it's possible is that, well, first of all, we let the customer create the bill. So the customer first creates a bill. And by that, I basically mean that the customer chooses some random serial number. And then she creates this string S, which says that this is a bill, blah, blah, and the serial number is this serial number that I've chosen. And then she computes the hash of this bill. So if the bill is S, she computes hash of S. And we can use any hash function here. So you can just imagine that we're using one of the standard hash functions, for example, SHA-256 or anything, any other hash function that exists in Ethereum. Okay. And now there's a really good question in the chat. The question in the chat is, what if the serial number is duplicated? And the answer is that that's highly unlikely. So we are going to make the serial number really large. So for example, in this case, I'm saying that it's 10-digit and it's alphanumeric. So every digit has like 36 different possibilities. So if you really choose randomly, it's very unlikely that you get the same serial number as someone else. But generally, what we will see later on in this protocol is that if two deposits use the same serial number, then one of them will lose their money, basically. But yeah, we're going to assume that the serial numbers are unique because, again, we're just going to use a really long serial number and it's chosen randomly. So if you make it long enough, then the probability that you have the same serial number as someone else tends to 0. Okay. Now, so this is the part that I talked about. So anyone who can provide a valid bill and a signature on the hash of this bill will be paid 100 euros. So the bank pays you 100 euros as soon as you can give them a bill and a signature on its hash. Now, how does this look like? Well, of course, the bill itself is S. And when we were talking about signatures in RSA, we said that to sign something, you just raise it to the power of D. So the signature would just be the hash of S to the power of D. And of course, all the calculations in RSA are modulo N. So if someone can give these two things to the bank, then the bank will pay them 100 euros. And also, to avoid double spending, the bank keeps track of the serial numbers. So whenever, if you go to the bank and say, here's a bill that you signed, and this is the serial number, and this is your signature on it, the bank would pay you. But if you go to the bank again with the same bill that has the same serial number, the bank would say, no, this is double spending, I'm not going to pay you again. Okay? And this is also the problem that would happen. If you have, if you randomly generate the same serial number as someone else, then only one of you can withdraw. But again, we're assuming that's very unlikely. Now, so here's the part that really gets interesting. So the customer wants the bank to sign this hash, but she wants the bank to sign this hash without the bank actually seeing what it is that they're signing. Okay? So what she does is that she first changes this hash. So she just chooses some random number R, and then she computes this H prime, which is the original hash times R to the power of E. And E is basically the public key of the bank. Okay? And then she asks the bank to sign H prime. So the way it works from the point of view of the bank for signing is that whenever someone gives them 100 euros and tells them to sign something, they will just sign it. They don't care what it is. So they see H prime. They don't know what H prime means. But as long as someone pays them 100 euros, they just give one signature for that 100 euros. Okay. So this H prime is signed by the bank. But let's see how that looks like. So again, we said that signing is basically the same as raising whatever you want to sign to the power of D. This was what we saw in the RSA signatures lecture. So when the customer gives H prime to the bank, the bank would just raise H prime to the power of D and give it back to the customer. But what is H prime to the power of D? So H prime itself was the hash H times R to the power of E. So H prime to the power of D is just the hash to the power of D times R to the power of ED. But here's the thing, when we were talking about RSA, we basically said that, well, this is encryption and decryption, right? So raising something to the power of D is doing decryption, and raising something to the power of E is doing encryption. So if we do both of them, we get our original value back. So R to the power of E times D is just R. And of course, H to the power of D, we keep that. So if the bank signs this H prime that we gave them, what we will get is H to the power of D times R. But what did we want? We wanted H to the power of D, because that's the signature on the hash that we need. So what we're getting is just a factor of R different from what we actually wanted. So what we can do is that we can just divide this by R, or in other words, we can multiply it by R inverse, which is the modular multiplicative inverse of R. And this would give us a hash of S to the power of D, which is what we wanted. This is a valid signature on hash of S. So basically, what we have here is that the customer needs a signature on hash of S, but she doesn't want to give the hash of S to the bank. So she first chooses some random number, and we call this the blinding factor. In a sense, she creates another hash H prime for the bank to sign, and this H prime is the blinded version of H. So a bank who sees H prime cannot know H because they don't know this random number R. This random number R is something that only the customer knows. But at the same time, as long as the bank signs this blinded signature, this blinded hash H prime, then the customer can get that signature and just divide it by R because the customer knows R, and they will get a signature on the original hash that they wanted. Okay, so the bank signed something without getting any information about it, and now the customer or the recipient, whoever wants to withdraw the money, can just go to the bank and show them this banknote or bill S, and also the signature of the bank on the hash of the banknote. And now the bank can verify that this is actually a correct signature. But what the bank cannot do is that they cannot figure out which one of these H prime values actually corresponded to this H value here. You see, so if, for example, there were 1,000 deposits in one day and then 1,000 withdrawals, the bank can verify that each withdrawal is correct and it's unique. So because they can verify their own signature and they can verify the serial number, but they cannot connect any of the withdrawals to any of the deposits. So from the bank's point of view, all the deposits look the same and all the withdrawals look the same. So this gives the customers a lot of privacy. Basically, imagine that you can transfer money from your bank account to someone else's bank account, but the bank has no way of telling who transferred to whom. They will only see that some money went out from your account, but the same amount of money also goes out from many different accounts in the same day. And then they also know which accounts have received money, but they don't know the correspondence. They don't know who paid whom. Okay. So this is the really nice protocol that was actually designed much before Bitcoin. It was designed in 1983, which is amazing. And so as you see, this is kind of like a cryptocurrency. It's like a better version of Bitcoin in terms of the privacy that you have, because on Bitcoin or on Ethereum, when you transfer money, this transfer gets recorded on the blockchain, and then everyone in the world can see it. Everyone can know that a person with this particular public key or this particular identity sent this much money to someone else with this other identity. Completely transparent and public on the Bitcoin blockchain and also on the Ethereum blockchain. But what we see here is that this is giving a really high degree of privacy to the transactions. But of course, the downside here is that we have a system that is centralized. So we have a single bank, and this bank basically gets to have a say in every single transaction, right? So for example, if the bank decides at some point that they don't want to honor their promise, that even if you give them a valid signature, they don't want to pay you, they can, because this is a centralized system. Of course, in the real world, if something like this is implemented, then you can also go to court and show the signature and so on. But how can you prove, for example, if the bank claims that you're doing double spending, how can you prove that you're not? And that's the problem here. So we are really trusting the bank in this system. But now what's your project? Your project is something a bit more complicated. So what I want you to do is that I want you to implement a mixer. And we've seen examples of mixers in our homeworks before. So a mixer is basically a smart contract where anyone can deposit some money. And let's say that we fix the amount of the deposit. So let's say anyone can deposit 1 Ether in this smart contract. And then let's say that they can collect it back using a different identity. Now, why do we want this? Generally, because of the privacy and de-anonymization problem that we have. So I've talked about this scenario before, that suppose you use cryptocurrencies such as Ethereum or Bitcoin to pay for some real world services. So let's say you go to a coffee shop and buy something using Ether, or let's say you maybe go to some online shop and maybe you buy a laptop using Ether. What would happen in these cases is that you create a transaction on the blockchain that pays the amount in Ether to the seller. So the seller would see this transaction. The seller would know your public key on the blockchain, your identity on the blockchain, because it's included in this transaction. But on the other hand, the seller also knows your real world identity, right? Because if you're buying, for example, a laptop online, you're at the very least giving them your name and address so that they can ship the laptop to you. So this creates an immediate problem. The seller can connect your real world identity to your blockchain identity. And then because all the transactions on the blockchain are public, they can just go through the history of the blockchain and find all the transactions that you have done with the same public key. So this is really terrible in terms of privacy. Imagine like every time you go to a shop and buy something using cash, what would happen if the shopkeeper could just know all the transactions that you have ever done? That would be ridiculous. So now the solution that we have is that we want to use a mixer. So this is a smart contract where you can deposit 1 Ether using some current identity that you have, and then you can use some new identity to withdraw this Ether. And again, the property that we want to have is that we want to make sure that no one can connect the deposits to the withdrawals. Okay, so I want to be able to deposit 1 Ether into this smart contract, and maybe after 24 hours or 48 hours, get this 1 Ether using a different identity. But I want to make sure that, assuming that a lot of people are doing the same thing, assuming that a lot of people are depositing and withdrawing from this smart contract, no one on the blockchain can connect my deposits to my withdrawal. Okay? And of course, this is your project. You have to write a smart contract that achieves this. And I've given you a lot of ideas here. Basically, your smart contract should use blind signatures and something similar to Chom's protocol here, which use RSA blind signatures, but you have to figure out how to implement this as a smart contract. And that's the hard part of this project. Okay, so you have to make sure that your contract gives a bunch of guarantees. Okay, so you have to make sure that no one is able to withdraw the same deposit twice. So this is the same as saying you don't have double spending. And you have to also make sure that no one can de-anonymize the customer and link their identities together. So of course, the customer herself knows her new identity and her old identity, but no one else should be able to make the link. So what everyone else should see is that there are maybe 1,000 different people who are each depositing 1 Ether into this contract, and then there are 1,000 withdrawals, and no one should be able to say which withdrawal corresponded to which deposit. Now, here's the part that I just want to go over the requirements and clarify them. So you can add third parties to your contract. For example, you can say, I will have someone who plays the role of the bank in my contract, or I will have someone who plays the role of the Paris branch of the bank, or the role of the Berlin branch of the bank. Okay, that's fine, but you have to do it in a trustless manner. Okay, what does that mean? That means that we never trust any of these third parties. They are third parties, but they're not trusted third parties. So they shouldn't be able to steal anyone's money or make a connection between a deposit and its corresponding withdrawal. Okay, so what does that mean? For example, in the system here, the bank was trusted, right? So if I gave the money to the bank, this is actually what I would do here, right? I would give 100 euros to the bank and then ask for a signature. Now, the bank is trusted at many different levels. First of all, if I give them 100 euros, they can just refuse to give me the signature, right? That's one problem. The other problem is when I want to withdraw my money. So when I want to withdraw my money, I give the bank some banknote S and some signature on it. So what the bank can do is that they can just falsely claim that this is double spending. They can falsely claim that they have already paid out for this particular banknote with this particular serial number. So here, again, we're trusting the bank that it would not do such a thing. But in your project, you have to do it in a trustless manner. So you have to make sure that the bank cannot steal anyone's money. And actually, another thing that the bank might be able to do, and you have to guard against in your contract, and this is really important, is that the bank might issue more signatures than they should. So let's say, suppose that, for example, each deposit is for 1 Ether, and let's say that only 50 people have deposited in the contract, but somehow the bank has issued 100 signatures. So you have to also defend against this kind of malicious behavior from the bank. And you can imagine why the bank would do such a thing, right? So the bank can just issue some banknotes with some serial numbers for themselves, and then they can sign it. And effectively, they can use that to steal other people's deposits. So you have to make sure that this also does not happen in your contract. So you have to make sure that the bank gives exactly as many signatures as is required. And you have to make sure that if the bank provides more signatures than was required, then you somehow refund everyone or penalize the bank or something like that. And it would actually be really nice if you can make the whole thing decentralized as well. If instead of just having 1 or 2 third parties that have the role of the bank, it would be great if you can have many banks. But anyway, the details are up to you. The most important thing here is that you have to do it in a trustless manner. So we don't trust our bank, and we assume that the bank would basically screw us and steal everyone's money or anyone's money that they can steal. So you have to make sure this is not possible. So there's a question in the chat. Do we need to handle the problem of having the same serial number as you mentioned before? No, just assume that the serial numbers are all distinct. And the way you can create distinct serial numbers is actually quite easy as well. So you can just take your name and add some random number to the end of it, and then take its cryptographic hash and say that this is my serial number. And it would be very unlikely that someone else has the same serial number, because that would then lead to a clash or a collision in the hash function. So generating different serial numbers is not really a problem. And you can always assume that all the serial numbers are unique. Okay. So what you have to do is that first, you have to send us a PDF file that explains your solution in detail. So again, this was a problem that we had in the previous homework. Some people did not submit the PDF file. We weren't too strict in the homeworks, but here we will be strict. So you have to submit the PDF file and explain. And you should, of course, also argue why it has the security properties that we required here. Now, the second part is that I want you to, of course, implement it in Solidity. And in this part, you have to also make sure that your code does not have any of the common vulnerabilities. So make sure that, for example, it doesn't have this transfer vulnerability that I talked about today, or any of the other vulnerabilities that we've talked about in this course. Okay. And then we also have some extra credit as usual. So the first part is to basically make your approach decentralized. What does this mean? So what I imagine is that many of you will just implement a smart contract that includes a bank in there. So there would be a third party that actually works as the bank and does whatever the bank used to do in Chom's eCash. But then the problem with this kind of thing is that what happens if the bank becomes unresponsive? Or what happens if the bank stops giving you services? So in those cases, your smart contract would basically become useless because the bank has stopped giving services. So one thing that can make it much more interesting is if you can have a decentralized approach. If you can have an approach where you can have as many banks as you like, let's say. Suppose that you have a smart contract and anyone can sign up in this smart contract to become a bank. Okay. So if you can do something like this, you will get 5 points in extra credit. And again, all the requirements stand. So it has to be trustless. So if you make it decentralized, but then the trade-off for making it decentralized is that you allow some of the banks or some of the other third parties to actually do some attacks, then you will not get any points for this part. Okay, so that's the first point here. Now, the second extra credit part. This one is actually about a very specific quirk of Ethereum. So we've talked about this many times, that in Ethereum, generally calling a function in a smart contract is a transaction that goes on the blockchain. And we talked about transaction fees. We said that we actually use gas instead of a fixed transaction fee. So what this means is that if someone wants to call a function in a smart contract, they have to have some money in their account, right? Because at the very least, they have to pay for the gas. But now again, imagine the scenario that we're using in our mixer. We have some money in some account, and we want to transfer this money to a new account, but we want to do it in a way that there is no link between the two accounts so that we get more privacy. And that's the whole reason why we're using this mixer. Now, I can use my first account to deposit the money into the mixer. That's fine, because my first account already has money in it. But when I want to use my second account to withdraw the money from the contract, I will need some money in my second account already because it has to pay for gas. So normally that would be fine. But in this extra credit part, I want you to solve this problem. I want you to make sure that I can get my money even if I don't have any money in my second account, even if my second account cannot pay for gas. Okay? So I want you to find a protocol and a solution that does this. And again, here you can introduce even more third parties. But again, you can do this, but you have to do it in a trustless manner. We don't trust anyone in these contracts. And we just assume that everyone is an attacker. So another assumption that you can have here is that you can also assume that the participants can somehow send each other messages. So you can assume that there is some online forum, for example, where everyone can post anonymous messages. And whenever someone posts a message, everyone else would see it. But of course, these messages are anonymous, so they will not be able to see who this message comes from. Okay, and again, please take care of all the requirements. So especially make sure you explain your approach in your PDF file, because that's something that the TAs really need. Okay, so one question in the chat is, how can the bank steal with extra signatures? Shouldn't the signature the bank generates for the customer have to match with the extra signatures? So here's the thing. Consider again this scenario here. Here, what would happen was that the customer was paying the bank, and then the bank would pay the customer again. So in this case, there is no incentive for the bank to generate any extra signatures, because if the bank somehow generates frivolous signatures and gives them out to other people, then that just basically means that more people can withdraw and the bank goes bankrupt. But what would happen if we implement this, for example, in our Mixer smart contract? Now, of course, this would depend on your particular implementation, but I'm just going to assume some general structure. So it's very likely that we're not going to pay this money to the bank, right? Because if we actually pay the money to the bank, then the bank can run away with the money, and then it's not trustless. So what's much more likely is that in your smart contract, you will keep the money inside the contract. But then taking the money out of the contract would need probably a signature from the bank. Now, this is the part where the bank suddenly has the incentive of creating new signatures, fake signatures. So suppose that 10 other people have actually deposited money. Now, if I'm the bank, what I can do is that I can create 10 banknotes for myself and sign them for myself, and then use this signature to take the money out from the contract and basically steal other people's money. So you have to make sure that this is not possible in your contracts. Okay. Yeah, and there are also some notes and tips here. Yeah, another point that I wanted to say is that generally we assume, again, I'm repeating myself over and over again, but this is the most important point, and this is something that many of you did not really take into account when you were doing the previous homeworks. And since there are no resubmissions for the final project, I have to explain this over and over. So you should assume that everyone is an attacker. Okay, so everyone is an attacker, but they're rational attackers. So what that means is that everyone is trying to just maximize the amount of money that they can make. And if your protocol enables someone to steal someone else's money, you have to assume that they will do it. Okay? But at the same time, what this means is that if you introduce new third parties, for example, if you say someone has to act as the bank in my smart contract, then you have to make sure that you pay some fees to them. Of course, these fees can be small, but there should be some transaction fees or some small fees for the services. Otherwise, the third party has no incentive to do the service. So for example, if in your contract you have a function that has to be called by the bank, what that means is that the bank has to pay for gas money to call that function. So you'd better make sure that they get some fees that actually are larger than the money that they have to pay for gas, because otherwise no one would act as the bank in your contract. So what this means in practice is that you have to pay some money for the mixing service. So if you deposit 1 Ether, you will probably not receive 1 Ether on the other side. You will probably receive like a little bit less, but that's fine. So it's fine if every person has to pay some small amount of deposit. But again, another point here is that just like in the homeworks, you have to make sure that the values that go in and out cannot be used to de-anonymize the people. So one thing that I would suggest is that you say everyone deposits 1 Ether and can get, for example, 0.99 Ether out. So make sure that the amount that they get out is the same, so that no one can use the output amounts to actually figure out which deposit this was. Okay, so yeah, that's it for today. This is the end of this session. I will stay and answer questions, but you don't have to stay. In this course, I just wanted to cover one more topic, which was verifiable secret sharing. Unfortunately, since a lot of our sessions landed on holidays, I didn't have time for that, so I will just put up a video about it. And yeah, the last point is take part in the SFQs. The student feedback is really important, especially because this is the first iteration of this course. So in a sense, if you hate the course, the worst thing you can do to the course is not taking part in the SFQ, because that would mean the course will not be offered again. But if you really like the course, please take part in the SFQs, because if we get a lot of participation there, then the course will become a regular course and we will have it every year. Okay, so let me go to the chat and answer the questions now. What if the contract itself makes the signatures? So this is actually a very good question, and it's something that is probably impossible. So I don't know, maybe you can come up with some clever cryptographic tricks that really allows the contract to make the signatures, but normally this wouldn't work. And the reason that it wouldn't work is that in order to create a signature, you need to know a private key. You need to know the secret key, right? And if your contract knows something, then everyone knows it, because we've talked about this before. So anything that goes on the blockchain is public. If you have, for example, a variable in your contract that contains the secret key that is used in the RSA, then if the contract can access it, then everyone else who can read the blockchain can know the value. So that means that if the contract can sign something, then everyone on the blockchain can know the secret key and can also make fake signatures using that. So you have to be very careful about this. And this was actually a very common error in the homeworks as well. So people assume that, for example, if you use the keyword private in your contracts, that the data is actually private. It's not actually private. So what private means in Solidity is that other contracts cannot access it. But it doesn't mean that people who are just looking at the transactions on the blockchain cannot see the value. So nothing is private on the blockchain by default. And actually, one of the really important points that I have to say is that when you write smart contracts, never store secret keys in the smart contract. It's fine if you store public keys in the smart contract, because public keys are public anyway. Everyone is supposed to know them, but never store secret keys inside your smart contract. Okay, so another question is, what if a node loses some fee to tamper to make a lot of other nodes also lose money? Okay, so generally we can have two types of attackers or two types of adversaries when we are analyzing our smart contracts. We usually talk about rational adversaries and malicious adversaries. So rational adversaries are adversaries who just think about maximizing their own payoff. So what they care about is to make more money. And if there is an attack that makes them lose money, they will not do it, because they just care about their own payoff. They're rational. Now, the definition of a malicious adversary is that they just want to hurt you, or they just want to hurt a particular user. And they don't care how much money they themselves lose in order to do this. Now, usually the requirements that we have is that our contracts should be safe and secure against both types of adversaries. So, for example, in the homeworks, again, going back to the rock, paper, scissors example that we had in homework 4, a lot of you did not get 10 out of 10 there because there were situations where one party cheated. For example, one party did not reveal their choice, and then the money of both parties got tangled up and locked up in the contract, right? So that's a case where you have a malicious party, and the party is willing to lose money just to make sure that the other party also loses money. Now, in this particular case, only for the final project, we are not considering malicious adversaries. We are only considering rational adversaries. So this makes the problem much easier. So the answer just for this final project is that if you find an attack that makes the attacker lose money, then the attacker will not do that particular attack. Of course, it might be that the attacker can do some other attack that doesn't lose them money. But again, this is only for this final project. When you're writing smart contracts in the real world, you have to assume that you have both types of attackers. So you have to make sure that your protocol is safe against any attacker, especially against malicious attackers. Okay. So someone says, thank you for the course. Okay, thank you for taking part. So another question is, can we assume that if we include many third parties, they will not all collaborate to steal the money? No, you cannot assume that. So this goes back to the problem of identities on the blockchain. So generally, you cannot know if two different public keys belong to the same person. So, this is actually a very great question, and I had to definitely clarify this. So because you don't know which identities belong to the same people, you have to just always assume the worst case. So if you have, for example, many different third parties, maybe you have 5 different banks, you have to assume that in the worst case, all 5 are actually the same bank, and maybe they're all collaborating together, and maybe they all want to steal your money. So yeah, you cannot assume that they're distinct people. So another question is, what is the use of the hash function? Oh, okay. So we're using the hash function here. Well, there are several reasons for this. One simple reason is that this is a long string, and instead of having a signature on a long string, we prefer to have a signature on a small thing, so on just a hash. But another point here is that we want to make sure that no one can de-anonymize, right? So let's again look at the point of view of the bank here. The bank gets this H prime, and we want to make sure that from H prime, they cannot get back to H, right? Now, if instead of using the hash of S, we just used S itself, then what would happen? Well, when someone goes there and again, we're just assuming that this S is somehow encoded as a number, right? Because we're working with RSA, and in RSA, everything are numbers between 0 and n-1. But if I use S instead of the hash of S here, then when I want to withdraw, when I go to the bank and give them the S and the signature on S, let's say S to the power of D, what the bank can do is that they can just look at all of the possible deposits that have been made and try to somehow figure out which one is more likely the deposits that corresponded to this withdrawal, right? So the bank can do some sort of statistical analysis, assuming that this random number was, for example, chosen uniformly at random. They can just look into all the inputs and see which one is more likely. It will probably not help that much. Probably we will still have the same level of privacy, but it's a bit suspect. So I would prefer it if we just hash it first and then give it to the bank, so that you see, there are 2 levels of hiding if you hash it. If you don't hash it, all of your hiding of information is really dependent on this random number R, right? But if you hash it, then the bank is only seeing this H prime. So even if they somehow figure out what your number R was, they wouldn't be able to reconstruct your banknote unless you give the banknote to them. So in a sense, this is giving us one extra layer of hiding. Again, I don't think it's explicitly necessary. I think everything would work even if we don't have the hashing, but it's just nicer to have the hashing. Okay, any other questions? Great. Okay, so finally, feel free to write an email to me if you have any other questions. And I hope you enjoyed this course. Take part in the SFQs. I'm repeating this many times. Please take part in the SFQs. We need the feedback. Okay. Oh, there's another question. When will we get the results of homeworks? So homeworks 4 and 5 are almost done. I hope that you will all get the results today or tomorrow at the latest. I think the vast majority of the students have gotten the results for homeworks 4 and 5. And then we're trying to give you the results of homework 6 in 1 week from now. But again, be very patient with this because we actually have very few TAs and it's a lot of work for them. And also about the resubmissions, we are first going to give you feedback on the main homeworks because you should have time to resubmit. And then we will grade the resubmissions after all the main homeworks are done. And another point is that generally don't worry too much about your grades in this course, especially after some of the grades for homeworks 4 and 5 were released, people were kind of stressed out. Don't be stressed out. The vast majority of the students are going to get A or A+. Everything is fine, especially because you get to do resubmissions. So at the end of it, your scores will be really high and all of your scores will be close to A. Okay, great. So have a great day. And once more, take part in the SFQs. I really need you to take part in the SFQs. Have a great day and bye.